Hello all and welcome back to this course on computer organization. So this is the final week of the course and therefore it is a good idea for us to focus on some problem solving. So the idea here is we are going to go through a couple of different types of problems, right? So that you get an outline of what is expected and how to go about solving these problems. And these are not just textbook problems, but they also indeed tell you how to do some things in real life. Okay. So the first thing is, in order to get a better understanding of the control unit and things like that, we are going to look at some problems like what is shown here. Suppose one of the following control signals in the single cycle RISC V processor has a stuck-at-0 fault, meaning the signal is always at 0 regardless of its intended value. So this could happen typically when the processor is manufactured, right? There is some manufacturing defect and for some reason that one particular line, metal line, which was supposed to be the output of a control logic, is now forced to 0 at all times. It cannot go high at all, right? And then we are interested in knowing, okay, suppose you got back a microprocessor manufactured from the fab like this, what are the instructions that are likely to succeed, right? Basically we are looking at the extended version of the single cycle processor that is shown here. Okay, so I'm going to reproduce that first of all at this location here. So let me get this, right? Let me get this processor out, this picture here. Okay, we are now talking about so we are going to look at the instructions. What are the control signals that are going to be stuck at 0? We are looking at RegWrite. Okay, so you come here and look at it. Don't worry about this blue line. I will highlight whatever I want specifically only in magenta. We are looking at this signal now. RegWrite is the signal that I am talking about. Okay, it turns out that this is stuck at 0. That means that signal can never go high. Okay, so how do you go about analyzing this thing? You just need to first look at where this control signal is going and then step by step backtrack and figure out which operations are going to get affected by this. So what you see first of all here, right, is that this is controlling the write enable 3 signal, and the write enable is basically the enable for the only write port of the register file. Remember, our register file had 3 ports, 2 read and 1 write port. That write port is controlled by write enable, which is now going to be stuck at 0, and therefore none of the operations in the microprocessor that involve a register write back operation can work correctly, right? Because this signal is never going to go high, and therefore the kind of signals that the kind of instructions that I can think of which are now going to fail, right, are basically R type instructions. Okay, then we are talking about some I type of instructions as well. Remember, the register read is going to work correctly because none of those signals actually even require a control signal. You just provide the address A1, A2, those registers will get read out correctly, the operation will get performed, and the data also will come back. The result signal from the output of the ALU will come out correctly and will come back to WD3 perfectly. However, it's only the W enable signal that will not go high because RegWrite is stuck at 0, and therefore all these instructions will fail. Okay, and also the load word instruction is also going to fail. Okay, right. So that's the first problem. The second problem on a similar line is basically going to be this guy. What happens if ALUOp 1 is stuck at 0? Okay, ALUOp 1. So therefore we need to again go back to our block diagram, okay, and let me use a different color, ALUOp, right. So where is this ALUOp going? So that is, we got to go back to a different figure for that, right. So you look at this, that is sitting inside this control block, okay. So you look at the control signal here. So let me get this over so that I can annotate on it, right. I'm going to get this over there. So let me put this here. So now we are saying that ALUOp, right, the ALUOp 1 is going to be 0, right. ALUOp 1 is stuck at 0. So which means that, you know, if I redraw this as 2 bits, right, this is my ALUOp 1, right, maybe no, I will draw it on this side so that it appears like the MSB. So this is my ALUOp 1, okay, that is now stuck at 0, okay. And how do you now figure out what kind of operations that is going to control? So for that you have to go in and look at this ALUOp table here, right. So if you look at it, we are saying that the ALUOp is basically going to go ahead and control, you know, the kind of operations that can be performed in this, you know, in the ALU, right. So if you look at it, this is a truth table that is going to tell you what kind of instruction is going to get executed, and it is going to generate this ALU control, right. So ALU control 2 to 0 is going to get generated depending on this ALUOp function 3 and all that. And therefore when ALUOp goes to 1 0, we are saying depending on the function 3, you can get various kinds of operations, add, subtract, you know, set, less than, all that, right. So what is going to happen is, typically none of these control signals, right, other than add can actually end up happening correctly. So that's the problem here. So in fact I would say, if you look at it, add and subtract that are needed for the load word, store word, branch on equal will happen correctly, right. But none of the operations that are associated with this 1 0 operation, 1 0 option will actually work correctly. So the ALU decoder is now going to have a fault, and therefore all of these operations are actually going to fail. Add, sub, SLT or AND, right. None of these operations can work correctly with respect to the ALUOp being stuck at 0. Yeah. So however, it's important to note that the add operation alone will work, because if you look at it, the ALU control 0 0 0 is generated either by 0 0 or 1 0. So as long as the ALU control is 0 0 0, the add operation will work. So the only operation that will work really, you know, for our type of instructions is the addition operation, right. None of the other operations are going to work when the ALUOp 1 signal is stuck at 0, right. So now let us go ahead and look at the next problem. So what happens if ALUOp 0 is stuck at 0? Okay. So again you come back here, you got to look at this whole table. ALUOp 0 is the lower bit, right. So we are now talking about this guy. If this is going to be stuck at 0, then obviously the only instruction that will fail is the branch on equal, right, because that subtract operation cannot be done. However, the if once it goes to 1 0, the subtract operation you know, can happen in the ALU, right, for the R type instructions. So that's the only thing that is really going to fail, right. Right. So likewise, if the memory write signal is now stuck at 0, right? Then what is going to happen? Again, you got to go back to the control signal here. We are now talking of the memory write signal. Sorry. Being stuck at 0 here, right? And therefore that's going to fail here. So what is going to happen if the memory write, right? So this is my fourth problem, memory write is stuck at 0, right? Stuck at 0, right? Then what is going to happen? It is basically going to control your write enable of the memory. Okay, so this basically means that no data can get written into the memory, and therefore all the memory reads will go through. That means your load word and operation, all that will go through. It's only the store word that is actually going to fail, and therefore I would say the only operation that will really fail is the store word operation that is bound to fail. Likewise, IMM source 1 and 0, right? You can see what is going to happen if these signals are all stuck at 0, right? So the procedure again is very simple. Come back here, look at the block diagram, trace where that signal goes in, right? So the IMM source is basically going to be controlled by this guy, right? This goes into my extender unit, right? And remember, that is depending on the instruction type that immediate data is going to get interpreted appropriately and is going to get used for various purposes. So you need to now track based on again that truth table logic, right? So if you go back here and you look at what are the kind of things that we were looking at here, right? So if you look at this immediate logic, right? So there was this immediate logic that we wanted to look at, right, in order to understand how the decoding is going to happen, right? So you look at this. This is the truth table that was being used by the IMM source, right? That was consuming IMM source, and we are saying now that IMM source 1 is stuck at 0. That means only the I type will happen, right? The branch I type and S type will happen correctly. The branch type of instructions are obviously going to fail if this signal is stuck at 0, right? So I will stop at that for this specific kind of problem. You can follow the same procedure and solve it for other cases as well.